All right. Hi, everyone. Welcome to the SC25 Student Cluster Competition Benchmark webinar. Thanks all for joining us. Today, we have Ryan DeRue from Purdue and Amia Madri from Purdue, and as well as some folks from ML Commons who will be talking today about all you can expect from benchmarks for the competition this year in St. Louis. So today we'll have Ryan who will be presenting. So with no further ado, kick it off, Ryan. Thanks for being here.
Sure. Thank you, Lamai. Can you confirm that you can see my screen?
Yep, looks good.
Okay, perfect. Okay, so good afternoon, everybody. Like Lamai said, my name is Ryan. I work at Purdue University, and I have been involved with the Student Cluster Competition for the past 2 years. This will be my third year. And every year that I've been involved, I've kind of worked on the benchmarking portion of the competition. So hence why I'm here to kind of talk about what that's going to look like this year. I'm also joined by my colleague Miro. Miro, if you want to introduce yourself.
Yeah, absolutely. So, as the affiliation say, I work for AMD, but I also spend part of my time working with ML Commons, the organization behind MLPerf. I'm a co-chair for MLPerf Inference Working Group. So so for this talk, I will be representing ML Commons as a sort of cross-industry organization dedicated to AI benchmarking, which is what would be part of this part of the benchmark at Student Cluster Competition 2025.
Perfect. Yeah. So I'm going to start with kind of talking about what the benchmarking tasks are going to look like. We'll talk about logistics. I'll talk about a couple of the benchmarks, and then Miro's going to move into talking about our third benchmark. So getting right into it, this year for the benchmarking portion, we have three benchmarks that we're going to be working with. Two of those are synthetic benchmarks in the form of high performance LinPack, or HPL. HPL has been used in the student cluster competition for years and years now. It's kind of the perennial, ubiquitous benchmark in the HPC space. And we'll also be working with a derivative benchmark of HPL, HPL with mixed precision. Later in this webinar, I'll kind of delineate what the difference between those two are. And then we'll also be working with an applied AI benchmark in the form of an MLPerf inference task. I'll let Miro kind of reveal what that is here later in the webinar. But that will comprise our three benchmark tasks. And logistically, what benchmarking is actually going to look like is the portion of the student cluster competition involving benchmarking is just going to be from Monday morning to Monday evening of SC. There's more detailed logistics that have already been covered in one of the earlier webinars Lamai gave. I linked to it here. The slides will be available so you guys can navigate to that. But essentially, from Monday morning to Monday evening, what we're going to be doing is essentially having each of the teams configure their systems to achieve the best performance from each of the benchmarks that we mentioned. So you guys are going to be configuring your systems for that, submitting artifacts proving that the performance that you saw from your benchmarks you actually achieved. And then we'll use those artifacts to kind of give you guys an aggregate score for the benchmarking component of the competition. So there'll be more detailed submission instructions that will be shared later. I ask that when those are shared, you read through them very carefully and make sure that we follow them carefully, because we do plan to use scripts for automated grading. And if files aren't named what they're supposed to be, or folders aren't located where they're supposed to be, that will cause the scripts to misbehave, and then it'll be more work for us and more work for you. So just make sure when those things are shared, you give them a read before the competition. But essentially what we're going to be looking for is artifacts that show that, when you were running your benchmarks, you stayed within the power budget and that your hardware configuration didn't change between benchmarks. So after you've submitted your benchmarks, you'll ask that we go and certify your cluster, and we'll be checking for exactly those things. We'll have a time series plot of your power utilization over the course of the benchmarking portion. We'll make sure that you stayed within the 10 kilowatt power budget for all three benchmarks. If you do go above the 10 kilowatt power budget, you will lose, or that run will be invalidated, and you'll also be docked some penalty points on the aggregate score. And once we have certified your cluster, you aren't allowed for the remainder of the competition, so both the benchmarking portion and the subsequent 48-hour competition, to change your hardware configuration or reboot any node. We will allow you to, as long as the benchmarking portion is still going on, so before the end on Monday evening, you can resubmit a single benchmark, and normal penalties will apply if you go over power budget after certification. So if you go after or over power budget after certification, any benchmark during that period would be invalidated, and you would receive that penalty against your aggregate score. So a few suggestions for everybody would be, one, familiarize yourself with these benchmarks ahead of time. Particularly with ML-Perf, there's more moving parts there than with the HPL benchmarks. And you want to make sure you understand what it is that we're actually asking you to do. If you try to show up to the day of a competition and you haven't looked at these things or attempted running them before, you're probably not going to have time to finish all of the benchmarks. Wherever possible, try to script and automate. For example, if you are doing HPL benchmarking and you're performing a parameter sweep over the HPL parameters, that's something that can be really trivially scripted. And so you should do that and not waste time, manually changing the HPL input files. And then lastly, vendor-provided binaries are allowed as long as those binaries are publicly available. And in fact, we would encourage that you actually use vendor-provided binaries where possible, because oftentimes vendors make hardware-specific optimizations to the reference implementations in ways that don't violate the rules of the benchmark. So as long as these are publicly available, you're allowed to use them. And in fact, I'll point to several of them later in this webinar. And I know that we have some returning teams from last year, so I just wanted to highlight a few of the changes from last year. There won't be a mystery benchmark this year, so you guys know all three benchmarks that we'll be asking you to perform. As well, there'll be no benchmarking interview this year. In the past, a portion of your benchmarking score has revolved around an interview that we do to kind of assess your theoretical knowledge of the benchmarks. That won't be a component of your aggregate score this year. And then finally, the power budget is being increased from 6 kilowatts to 10 kilowatts. So some of the scores that you might have achieved last year, you might expect other teams to achieve higher scores this year. So moving into the first benchmark, HPL, or High Performance LinPack. HPL is, I should amend this from one of the most popular benchmarks to probably the most popular benchmark in the HPC world. High Performance LinPack is used as the metric for kind of distinguishing the top 500 world's fastest supercomputers. So biannually, the top 500 publishes a list of the top 500 fastest machines in the world. And the metric that they use is the score that was achieved on the HPL benchmark. So the most recent list was published in June 2025. And El Capitan out of Lawrence Livermore National Labs achieved a score of 1.742 exaflops. Essentially what HPL is doing is it is generating a random dense linear system where all entries of that dense linear system are doubles or FP64 data types. And it's using matrix multiplication and other linear algebra operations to kind of solve that dense linear system. And because matrix multiplication and other linear algebra operations are so common in scientific computing and AI and graphics and a lot of the common tasks that computers are performing, we kind of use this score as a proxy of the performance that we would expect that computer to have on an actual application. And so the input to HPL is the parameters that we want to use to generate that random dense linear system and how we want it to be solved. And the output is the number of floating point operations per second, or flops, that were achieved by the machine. And so last year, for context, the best HPL score was achieved by Nanyang Technical University, and they achieved a score of 236.4 teraflops. But I'll caveat that and say that they performed that within a 6 kilowatt power budget, and this year the power budget will be 10 kilowatts. So HPL typically uses some basic linear algebra subprogram libraries. That's what BLAS stands for all of its linear algebra subroutines. So these are libraries that have very efficient implementations of your most common mathematical operations. The two most common ones people use are the Intel MKL, or Intel Math Kernel Library, and OpenBLAS. And so HPL will require that you use one of those BLAS libraries. It'll also require that if we're doing this over MPI, or using multiple nodes, that we have some MPI implementation for distributed memory parallelism. As well, our compiler should allow for OpenMP support anytime we are doing single node parallelism or shared memory parallelism. And HPL can take a variable amount of time based on its problem size. Its problem size is something that we determine in the input parameters. We're basically generating or describing the size of the matrix. And the size of the matrix is typically contingent upon the amount of memory that we have. The matrix has to fit entirely within our total memory, be that distributed or in a single node. And so that's going to be one of the parameters that we are giving in our input file. To build HPL, you can, if we wanted to run this on a CPU, we can just easily download and untar the source tarball from one of the links that you should be able to navigate to here. You can untar that tarball, load all of the necessary libraries for the BLAS routines, as well as make sure that we have an appropriate MPI implementation and compiler, and just run. It comes with a really simple configure script to configure and build the make file and actually build the binary. And once the binary is built, we just add that to our path. The binary is by default named XHPL. So we'll see that in the documentation for a lot of the vendor-specific implementations. And so if I built this on the CPU, I could invoke the executable with just XHPL. But typically what you guys are going to be doing is, because I expect that you'll be running HPL on accelerators, is NVIDIA and AMD both provide containers for launching HPL on their GPUs. So as opposed to building this from source yourself, you could navigate to their distributions. NVIDIA has containers in NVIDIA GPU Cloud, and AMD has containers in Infinity Hub, and just kind of pull down their binaries that way. But regardless of whether you're running this on a CPU or GPU, your HPL input file is going to look the same. So whenever you invoke the executable is going to look for the presence of this hpl.dat file in your current working directory. That hpl.dat file defines how we want to generate our random linear system and how we want it to be solved. There's some references that I link to in this that will describe all of the parameters that are available in that input file. But the most important ones that you guys are going to be tweaking are the array size. So we're generating an n by n matrix. So your array size, this value of n, is going to be the thing that we change based on the memory that we have available in our system. NB here, the block size, is essentially the size of the chunks that we want to perform linear algebra operations on at once. And our P and Q describe essentially the processor grid we want to create. So if we have a really large matrix, you can kind of envision dividing this up into a grid, and we have a certain number of rows and a certain number of columns. Our rows and columns, P times Q, needs to equal the number of MPI processes that we are invoking for actually solving this system. So for example, an invocation might look like this: MPI run dash NP2, and then the executable XHPL. This would require that we have a P times Q equal to 2. Typically, when you're running this against GPUs, your processor grid, or your dash NP here, is just going to be equal to the number of GPUs that you have. So you'll experiment with what changing each of these parameters does for the performance of your system. There's some kind of rules of thumb for tuning HPL. If we're running this on a CPU, typically we want the matrix to occupy 80 to 90% of our overall memory for optimal performance. If we're running on GPUs, oftentimes this memory is closer to 90 to, I wouldn't say 100%, but more like 98% memory occupancy. There is a reference here that provides a calculator for if you basically give the amount of memory that you have on each node or each GPU and how many of those nodes you have, it can give you a decent starting point for your value of N and P and Q. And then your block size also impacts performance. You'll want to vary these different block sizes to kind of see what provides you the best performance. A lot of times it depends on your architecture or GPU type. So if we're running on a GPU, usually your block size will be slightly larger. If we're running on a CPU, typically your block size will be proportional to like your L3 cache. So you'll have to experiment with your values of NB to kind of figure out what gives you the best performance. And the exact layout of your MPI processes or OpenMP threads also impacts performance. And a lot of times you'll find that the optimal layout is more closely aligned to like a square of processor grid. So for example, if I had 16 MPI ranks, I would usually expect like a 4x4 processor grid to have better performance than a 16x1 or a 1x16 processor grid. Okay. And like I said, there's some resources here that you can click through. These slides will be posted. This advanced clustering, this third one, is the tuning calculator that I alluded to. These other ones provide you know, other information that's probably useful for you as well. Okay, so the second synthetic benchmark that we're going to talk about is HPL mixed precision, or HPL MXP. This is essentially a derivative benchmark of the original HPL implementation. But it was developed as a result of the kind of shift that we're seeing in modern computing towards reduced precision arithmetic. And what I mean by that is 10, 20 years ago, FP64 computing, or full double precision computing, was kind of king of the scientific space. We found that, in order to do, multi-body physics problems, or various other types of scientific calculations, we needed the full the full precision afforded to us by using a 64-bit data type in order to achieve maximum accuracy. And so that's what all hardware was kind of designed to do. In the advent of AI and ML, we've seen that in order to achieve the same types of accuracies in models, we don't actually need that full 64-bit precision. And so a lot of the hardware vendors who manufacture GPUs have started reducing the amount of support on those GPUs for FP64 data types to more reduced data types like FP16 or FP8. And so HPL mixed precision is essentially taking the old HPL benchmark that's been used for decades and transforming the factorization step of the solution to that dense linear system to use FP16 factorization. And so this tends to run a lot better on modern GPUs that are now allocating more of their limited literal circuit space to FP16 type operations. And so the factorization is performed on this reduced precision. And then at the end, the solver has kind of a refinement step to bring the solution back to 64-bit accuracy. And this is a relatively new benchmark. There's a separate top 500 list for the HPL with mixed precision that's published along the same biannual cycle as the original top 500 list. And you can kind of see here, well, El Capitan has the highest spot on both lists. That's not necessarily true for the rest of the systems. If you look here, the second on the HPL mixed precision list is third on the top 500. The fourth is actually 15th on the top 500. So this is a benchmark that is doing a much better job at kind of analyzing how accelerators perform against the data types that people tend to care more about in modern computing. And so the input to mixed precision HPL is going to look really similar to what we saw for standard HPL, but typically as opposed to having an hpl.dat file, we're going to be providing these options from the command line. So all of these options that we talked about for HPL have a command line analog. So like the n is transformed to --n. P, instead of P just defining the number of rows, we now have number of processors in the row. There's documentation for this that is linked in our references. But importantly, there's a few new required arguments. Typically when people are running mixed precision HPL, because it's looking at the data types that GPUs are better for, they're running it on a GPU. And so you have to also provide your GPU affinity, which is just a colon delimited list of the GPUs you want it to run on. And then we also provide a row or column major option to the input. One piece of advice that I'll give is there are a few more optional arguments, depending on the implementation that you use, that have effect on the type of MPI that is being used. So you'll want to make sure that you're using a GPU-aware MPI implementation, because you'll find that when we look at the actual options that are available for HPL MXP, that's not something that is just assumed without specifying more specific options. Just a hint. So there are a few mixed precision implementation options. If you wanted to, you could technically build this thing from source, but the reference implementation is not going to have nearly the performance that you will receive by just using one of the vendor-provided optimized implementations. So NVIDIA, AMD, and Intel all have containers that you could download and use for your systems. Intel names theirs a little bit differently. They call it HPL-AI. It's the same thing, mixed precision. And you can access that from these slides. But each of these implementations have slightly different optional arguments. You'll want to make sure that not only do you read the way that the reference implementation describes this benchmark, you'll want to take a look at the specific documentation for the implementation you choose to use, because their arguments do differ a little bit. And as a reminder, you are allowed to use any publicly available vendor implementations. Okay. So I provide a few resources here. These are basically everything that was hyperlinked in the earlier slides. So that comprises our first two benchmarks, both of our synthetic benchmarks. I'm going to hand it over to Miro for MLPerf.
Absolutely. Thank you, Ryan. So yeah, that's let's dive into second part of this, which would be the MLPerf benchmark for student cluster competition, and that would be llama to 70 billion inference. So let's move on to the next slide. So this is, I guess the what I would maybe start with is that the MLPerf is, I assume that most people are here familiar with MLPerf. MLPerf benchmarks are administered by ML Commons organization, which is a cross-industry organization that is actually dedicated to benchmarking and generally advancing AI. So ML Commons, there's several flavors of MLPerf benchmark. One we're going to be targeting here inference, but there's also training, and there are other parts of that. But specifically, we'll be looking at inference as a target workload for this round, or for this year's student cluster competition. We had some discussion which benchmark to use. Last time we worked on it. Last time I believe it was BERT. We decided to actually move to something newer. This would be llama to 70 billion inference, and this is currently the most popular MLPerf inference benchmark. The test that when people submit to MLPerf inference, there is MLPerf inference, the suite that comprises up to 10 independent benchmarks. And when people make submissions, they can pick and choose whichever ones they want. And this llama to 70 billion is actually the one that is by far the most popular. So this is something that you can find comparable data for, and given if you have and I think the chances are good that for teams bringing their hardware, they should be able to find comparison point and see approximately what performance they should expect. Also, given that this is an AI benchmark, an AI field is sort of moving pretty fast. Things are changing a lot, right? You should also expect that, and this sort of lends itself to sort of benchmarks that is fairly complex to execute. I've tried to put together sort of the things to make it easier, but teams should expect that it would require probably some preparation, figuring out some of these things. This is not the most intuitive benchmark, and again, working with MLPerf benchmark for a while, just trying to keep up with the latest updates, it makes it sort of difficult to balance sort of having things user friendly and being easy executed, balance that together with staying with the latest. So and as a result, there's some complexity and maybe non-triviality of executing. So I guess the first thing I would say is this would be the good workload to sort of try to test it ahead of time as a sort of best way to succeed. Now, the reason why we go with this benchmark, it's obviously the most popular one. It's well known, well tested. There are multiple implementations that have been done. NVIDIA have submitted, and also AMD, my company, has its own optimized implementation. This is also a model that Llama model in general are popular. They are licensed for free use, so that should be also fine. It's also a benchmark that performs really well. So because of all that, this is a good target. This is a good target to have, and that's probably one of the reasons why it's so popular for ML Camera submissions. Just to give you some more information on this, llama to 70 billion is obviously the model. The data set is, or the particular task that this is applied on is a Q&A, so question and answering, right? There are prompts, and the system needs to generate responses to that. These are based on open source, open ORCAD data set. And for MLPerf purposes, this is actually using a curated subset of this data set about the was it 24,000 samples. The ISL lengths are sort of are shown on the right hand side. If you want more information, there's a sort of blog that goes into some of the internals. I will sort of focus more on sort of practicality of execution. But again, if you want to know more about like what makes this benchmark work, here is a link for you. Let's move forward, Ryan. Okay, so one thing to understand is sort of, the way sort of MLPerf inference work is that you need to sort of understand there are certain tests, so that when you're sort of looking at what to do, you need to understand certain terms. And there are basically three basic things that come into play with Llama 2 or generally with MLPerf inference submissions. And those would be, there are two running modes, that there is offline and server. This should be sort of maybe self-explanatory, but what offline test means that this is a pure throughput test. So what happens in the offline test, you are given in the beginning a complete set of data, and then once you start processing, once you are given it, or once you start processing, the clock starts. When you finish, the clock stops, right? And basically the throughput, right? How many samples per time you were able to per minute or per second you were able to done. That is actually the metric, right? So this is just completely throughput test, and this is just completely throughput test. Is something that is easy to understand. There's another way of running which is called server. This is basically for your information. This will not be part of SCC, but this is sort of more realistic, but it's also more difficult to run, because normally when you would running these LLMs, you are not sort of given a set of tasks ahead of time. You could have requests that would be coming with certain frequencies, and you have to respond within certain predefined latency. So this time we are only going with offline, but please be aware that when you be looking at reference at implementation, that there are this offline and server. So please focus on the offline type of test. The other part is that would be required is that this MLPerf is not just about performance. You also need to satisfy accuracy. And so within the implementation we're going to be looking at, there is also a way to run in accuracy mode. So in accuracy mode, you basically need to run over the entire data set, and then then there are scripts that would sort of evaluate the result that get captured, right? And basically the accuracies are posted over here. You need to be better than 99.9% of the following Rouge scores as are given over here. If you are not, that actually would be invalid. So this is kind of a required sort of quality test that needs to be satisfied. Let's go ahead. Similarly, as Ryan mentioned for HPL, right? There are several different implementations. So there are that can be used, right? MLPerf inference has actually, I put in links, has actually a repository for the code and the specific code for Llama to 70 billion. But this is reference implementation. This is something that is provided sort of more of an example of code that should work on most devices. This is not really performant. It's fairly short. Which is preferable for people to start with and understand what's happening. But this is really not. I don't recommend using that, right? Similarly, as with HPL, I want people to look into optimized implementation. Basically, the way this works is that MLPerf allows submitters to basically completely rewrite reference code, as long as it satisfies model equivalency rules. So you need to be mathematically equivalent to the model. You can quantize, right? But other than that, you need to do the required operations, right? You can, however, You can, however, use framework of your choice. You can use this, or submitters can use whatever precision they like. And in fact, most of the and in fact, if you are staying within latest generation GPUs being on NVIDIA on AMD side, those things would be quantized and run in FP4. If you would be running on like older generation, like NVIDIA Hopper or for AMD 300, 325X, those would be done in FP8. Let's move on. Okay, so for SCC specifically, the ML, this particular test would require or Llama 270 billion benchmark requires to run on GPUs, and there are as a consequence of this being very popular benchmark, there are both optimized implementation for NVIDIA and AMD. I've put in locations where they can be found right now, where you can sort of find existing to get started right now. But I think the very important point at the very bottom of the slide, the way MLPerf works is that has a couple of rounds, or MLPerf inference has a couple of rounds a year, at which point the results, the updated results, updated codes will get released, and we are now very close to that point. So MLPerf inference 5.1 will get released in about 2 weeks on 9/9. Right, so all of these, so there would be sort of a new code available, and I would recommend everybody to look into that. Again, this will be one of the updates we can post, and we can give you the expected links where they would be. As of right now, those at that time, the 5.1 round is nothing is available, but then on September 9th, we'll have the new code and the results will be published. So this will be a good idea to use that. Okay, so how to run specifically? You basically for SCC25, you basically have two options. One is that you can take advantage of official ML or official MLPerf automation called MLC Flow, right? This is something that simplifies running. If you look into this optimized implementation, there are sort of multiple steps to follow, and it gets fairly complicated. MLC Flow is an effort to make that sort of more smooth, to make it run more smoothly. It currently has been tested with NVIDIA implementation. AMD will probably be added later. Again, this will be one of those updates. I gave you some of the link over here, but again, the MLC Flow will be updated for SCC with the 5.1 round in the near future. So please watch out for that. So that's one option. The other option would be basically just use the optimized code either from NVIDIA or AMD. And again, here is sort of I've put in the expected link where 5.1 would go. Again, we'll update it if this is wrong, but just expect that that would happen. And as I said, please remember there are these two options, and it's up to which one to choose. MLC Flow is probably a better choice because it's simpler. But if you sort of feel more advantageous and you want to sort of work at the lower level, it's fine to use the ML for optimized code just directly. Okay, let's go to the next one. So this is more on the automation. So this really just give you more example that they really automate multiple steps and make it things easier to use. It's better usability. There is a docs page link over here. And again, so this you may go ahead and want to start with this one. We'll sort of, as I said, there will be more updates for SCC. Sort of, we'll post later for the. So we want to have some of the things that MLC Flow will do for us specifically for SCC that we'll still have updates for you. Okay, let's go on to the next one. Okay, so one of the things that are very important in order to run this is AI workloads. So we basically wouldn't have two prerequisites. One of them is model, and another one is data set. So in order to because of the setting this up for the first time is time consuming, right? You need to download that, and in principle, in official instructions for MLperf code, what you would actually be instructed for is you would download the model, Llama 2 model, as was published by Meta, which I believe was published in as bfloat 16 model. You would need to go through quantization and everything. For SCC, we are actually trying to we are working into actually making this easier for you. We want to get already quantized model ready for you. That one, again, that will be one of those updates that we should have in the next few days. We plan to host have a place for NVIDIA quantized models. There is already a place. AMD itself has released their quantization at Hugging Face, so they should be available. But the advice here is, again, please watch out for this. And as a and because it's a prerequisite, it would be good, we strongly advise that you get both model and data set loaded on your machine, because before you come to SCC, so that you can go and do the runs quickly. And again, downloading a large data set or large model files is probably not a good idea on site. Let's move on. So what is required for sort of successfully completing what is expected? So that would be run offline and accuracy runs, right? We don't have to do the server. Now we also need to make sure that everything is valid. So when you run performance run, it should also tell you whether it's valid or not. Offline runs are almost always valid, so there should not be an issue. But you definitely want to make sure that your accuracy is being satisfied. Again, if you just take code as it is, I don't expect this to happen. But you need to watch out that you're running it the right way so that it works, so that you're getting valid results. And there is also another step that you would need to package and submit your result. There will be we will provide, as a part of the MLC flow, we'll provide a command that would do this for you. And that is one of the things we'll share with you later. And this is one of the last things I wanted to say. So the tips to be successful, as I said, keep in mind that this is that in AI world, things moving really fast. Things are difficult to set up. So this is complex benchmark in order to get started. So please do test runs before the competition. Just trying to do this for the first time. This is very difficult for beginners. So get some experience. Understand what are the prerequisites, what the things you need to have. You need to have what's the requirement, right? That what's the when you. How do you see whether your accuracy is valid or not? For example, what is the submission process, right? As well, and again, if possible, bring the data set and the model ahead of time so it's ready to go, and then you can just focus on execution. And very importantly, if you have any questions, please ask them ahead of time on the. I think there's a Google group forums. We'll try to get you answers. This is just a summary. So this would be a fairly challenging task. So I think that this is an interesting task, but it will be also challenging for the teams. This is a real ML per inference benchmark, real AI benchmark that is the most popular right now. Please use the optimized codes and sort of understand that what is necessary needs to be run. Understand that you need to get the result and also submit that, which pretty much mimics the experience the submitters for MLPerf have to do. So there's a certain level of understanding both this would be a benchmark that sort of exercises understanding of the AI as well as sort of understanding some of the processes. So please spend time on that. As I said, there are a few things that we will need to deliver to you later, so please watch out for that. And again, brand test when you can and ask questions early. If you come without sort of experience, it will be difficult to. We'll still try to help you, but it would be difficult to just sort of start from zero and get it running on a short notice. I think that's my last slide.
Okay, cool. So sorry, Lamai, I see that you turned your camera on. Were you going to say something?
No, I was just getting ready for for the rest of the show. That's all.
Sure. I was just going to say we have a couple of additional people here. So if there were questions that were in the chat, I haven't been looking. It doesn't look like there's any in the chat, but
No,
we're
there are
also happy to take questions now.
no questions in the chat, but Mary has her hand up. Mary, go
Hi,
ahead.
Mary.
Hey, everybody. Nice to see some good friends, and thank you to the committee for your hard work and really fun-looking challenges. I have a question from the very beginning, which is the comment made about a penalty as you're trying to benchmark and maximize your system under real conditions. I heard and I saw in the transcript that there'll be a penalty if you go over the power limit while you're trying to test out your system. And can you explain that a little bit more? It sounds harsh.
Yeah, so I believe that this is outlined in the, I can find a link here when I'm done talking, in the actual posted rules, but going over 10 kilowatts will just disqualify the benchmark that you're currently running on. It technically says that if you were to go above 11 kilowatts, that you could be like entirely disqualified. It uses,
Okay.
we'll say some flowy terminology, but 10 kilowatts is just enough to invalidate your current benchmarking run.
Okay.
Lamai, in terms of aggregate penalties for the entire score, not just benchmarking, were we going to be taking points off for going above 10 kilowatts?
Yeah, so for the benchmarking portion, as I think Ryan laid that out perfectly, and I think that has been done for many years now as part of the benchmarking certification, is that we invalidate runs if they go over the power cap. This has been done in prior years. As far as the penalties, Ryan is correct that if we go above the 10,000 kilowatt penalty, 10,000 kilowatt, 10 kilowatt power cap. I kept saying like I'm saying the wrong thing. Power cap, there will be penalties involved there. I have not finalized the rubric yet, and I'm hoping to be able to share out rubrics to the students' teams ahead of the competition. This might happen as closer or maybe farther into October as we coordinate with benchmarks, all the applications, and make sure that I have all the rubrics in hand. So I haven't finalized what that penalty rubric looks like yet, Mary, but I will be sure to surface that to the students so that they understand that. As far
Okay.
as the 11 kilowatt limit that Ryan referred to that is in the rules, that is pretty much like, hey, we don't want to go over this because we don't want the SC exec committee to be really angry at us for blowing up the convention center and then canceling the entire competition as a whole. So that one is just there really as a, hey, we want you to be safe. If we see you going over this, we will have stern words with you. I have not again finalized the rubric, but yes, it is very much, let's not go over this because we want to be good citizens and not have the exhibitor for set on fire.
Yeah, I appreciate that. 11 is a lot, and we would maybe be the first time SCC has brought down the center, but I understand during the, like, after, when the competition begins Monday night at 7 p.m., anything over 10 kilowatts results in a penalty. I got that. I've not been aware that there would be penalties during the benchmarking, the 9 to 5 p.m. benchmarking of the system. And so I'll be looking for those penalty guidelines that you guys would put out. What I'm hearing is you'll put out some guidelines for penalties that would be assessed during the benchmarking of the system on Monday from 9 a.m. to 5 p.m. Correct?
As far as penalties go, I think it's invalidation of runs, which
Okay.
can certainly be thought of as a penalty.
That's
Are there
normal.
other penalties, Ryan? And again, we
No,
haven't
sorry,
finalized
let
all
me
the
go back
rubric.
to that slide. I think I did a better
Okay,
job of
okay. Yeah,
explaining
thank
this.
you, Ryan.
Yeah,
I know about this, benchmarking, and it goes over 10, it doesn't count because it doesn't qualify your system.
right.
So that's why I wanted to clarify this.
Yeah, I had
Okay.
And as I mentioned, yeah, we haven't finalized all of the rubrics. I'll be talking to Ryan and Amia to say, hey, what are the finalized tasks? What's the rubrics there, and all the other apps. So once that's all in place, Mary, I will make sure that I'll share it out with the team so that they're aware what the possible penalties are. But
Awesome.
Ryan, go ahead if you had any more comments to add to that.
Yeah, sorry. So I phrased this pretty poorly. So this is a penalty after certification, since certification kind of locks in what your hardware configuration is. We don't expect that anybody would ask to have their system certified while they are, tailoring the upper
Okay.
limits of their HPL power draw. But once they have asked to be certified, because we do allow people to resubmit a single benchmark if they are going above power budget after their system has been locked. That's what would cause a penalty. So usually that matters more like for the actual 48-hour the application portion and repro portion and things like that. But technically after certification, they would receive a penalty if they go above power budget.
Okay, maybe this has always been this way, but thank you for that clarification for this. Once you certify, okay, that's very important to know. Thank you, guys. I appreciate it.
There's a couple of questions that came in through chat from Gowrie. I hope I'm not butchering your name. Thank you for the webinar. I had two questions at the moment. First, will we be expected to run all the benchmarks consecutively for the submission at SCC, or can we pick and choose run? I think that's in reference to some past benchmarking runs required that the benchmarks were run in a specific sequence I think this was not last year or the year before that, but in other years. And then second question was, for ML Perf, will we be running the full 24.5 K subset, or would we receive variants with smaller sizes like last year?
Yeah, so really the spirit of the rule. So I'll answer number one, and then I'll hand number two over to Miro. The spirit of the rule for number one was really we didn't want people, configuring their system one way at, 9, 10 in the morning, and then like in the afternoon, they have reconfigured their system to perform better for a different benchmark. And so that's why things were kind of asked to be run consecutively. I think in the past, we have accepted submissions that required us to go in and make sure that there was no reboot done on the system in between the two runs. And that the hardware was the same. We're trying to make it so that the artifacts that we request would prove that the system hasn't been rebooted or anything like that. So I don't think that we're going to actually require that everything be exactly back to back to back. But like within reason, we don't want a run at 9 in the morning and then another one at 5 p.m. If that makes sense. Amia, I see you turned your video on. Do you have any more context to add to that?
Yeah, I think you captured it perfectly. Thanks, Ryan.
Yeah. Miro, do you want to take number 2?
What's the number 2?
For MLPerf, will we be running the full 24.5K subset, or would we receive variants with smaller sizes like last year?
No, this would be this is fairly quick, right? In fact, if you do like H100 number, I think it's the 24K samples would take about 5 minutes, I think. So in fact, most of the, I think that, and the way MLPerf works is that you have to have at least 10 minutes run. So I think the expectation is that, in fact, it would be, you probably be, but that sort of gets figured out automatically how much samples you get. So you'll probably get some sort of multiple of that. But again, in terms of like time consuming, this is not a time consuming benchmark unless you're using something that is very, very slow.
All right, we're at the end of the hour. Thank you all for attending. Thank you, Ryan, Amia, Miro, for presenting. If you all have any questions, please feel free to drop them in the Google group. I know that Amia and Ryan and Miro have other avenues. I believe the GitHub org will also be populated with some tasks there, and we'll be ready for you guys to open issues in. Amia and Ryan, I'm sure will make an announcement for when those are ready and where the appropriate channels you can ask questions. But for the time being, feel free to reach out to us in the Google group. Right. Thank you, everyone. Thanks again, Ryan, Miro, Amia, and we'll see you all the next time.
Yep. Thanks for organizing this.
Of course.
Thank you, Limai.
Bye.
Thanks, all.